So in the previous lesson, we introduced the energy topic, the huge energy topic, and we talked about the energy consumptions in Europe, in several countries, in Italy, of course, and the penetration of renewable energies in global energy consumption, and also in the most important sectors like electricity, or the mobility sector, or heat and cooling energy for buildings and for industries. We also introduced the definition of biomass, and the very close connection between biomass and subproduct and residues, and also the connection with waste. So two families, biomass and wastes, that have some point in common, but the subproduct connection can move from waste to biomass. It's the point of contact between these two large families. We also talked about the typologies of biomass we have available for energy and also the biochemicals in general purposes. The sectors where we can supply biomass from residues like agriculture, forestry, agro-industry, and then we also start to speak about the step between biomass and biofuel. So how can I make biomass, which is a very large kind of possibilities, from trees to manure of some animals, to prunings, to straw, and so on. I have to transform this biomass into a biofuel, so a fuel I can use in an energy transformation system. And for example, and you can see this graph, we talked about chips, pellet, wood, of course, compared to fossil fuels like methane, or diesel, or gasoline, and other traditional fuel. And also we just have a look to a cost that in general is lower than fossil fuels. Also, if you have a very long pathway, because you have to start from field, from forestry, to collect biomass, transport to other places, transform it. So there is a cost you have in the biofuel, but also in any case, in general, this cost is lower than fossil fuels. Also, of course, compared to energy content. And this is the main topic we talk about today. So what are the main characteristics of biomass we need to know to work with biomass. I mean, of course, make research, make also some design activities, for example. So if you work with biomass, you should know some characteristics, chemical physical characteristics, and this is the topic of the first part of today's lesson. And we start with a very elementary picture, but it's the most easier way to start to talk about some characteristics. When we talk about biomass, you see a piece of wood, but of course you can think about every kind of biomass we saw in the previous lesson. Every biomass consists of three main parts. Water. We have water quantity in biomass. Is a very variable element, but present in every kind of biomass, and we need to consider a unit system and something like methodology to evaluate the water content, or we can also call it humidity or moisture. Okay, this is the methodology, and we will see the methodology to measure moisture. So water, an organic matter. Okay, the organic matter consists of several polymers like cellulose, for example, hemicellulose, lignin, and also other sugars, simple sugars, and so on. And then inorganic matter. So, for example, metals, and during an energy process, I find the large part of inorganic matter into ashes. So, if I burn, for example, biomass, the residue of this process is ashes, and ashes content some salt metals, and this is the inorganic matter. Okay. The organic matter, the organic part, usually is the most interesting part of biomass for energy purposes. We can use this part to produce directly energy, and you can see the flame that, of course, synthesize the energy processes, but we will see that there are a lot of possibilities to transform this part of biomass into biofuels or bioproducts. And of course, we can transform these parts into, for example, sugars, and then into alcohol, so producing the green substitute of gasoline. Or we can obtain, for example, bioplastics through a pathway we will touch in the next lesson probably. So this is the most interesting part. But of course, also these two elements are fundamental. Water is usually something not residual in the biomass, but it's present. And also ashes in general are considered a residue, but in the vision I'm trying to give you of circular economy, also ashes could be a feedstock for other processes. Of course, the organic part consists of three main elements: carbon, hydrogen, and oxygen. Of course, they are connected in very, very long polymers like cellulose, semicellulose, and lignin. But of course, I could have also other elements, nitrogen, of course, but also chlorine and sulfur. And these are considered a problem for biomass, because of course we can after the energy process we can find these elements in some pollutants. Emissions in atmospheres like nitrogen oxidase or sulfur oxidase or dioxins and so on. So a lot of pollutants I have to control before find them in atmosphere. And of course also ashes are considered a process residue, and we can find this part like ashes at the end of the process, but also they can follow the emissions in atmospheres, and so became a very dangerous pollutant, because very short, very small ashes like PM10, PM2.5 are very dangerous for the environment and also the human health. And another way to see these three main part is shown in this picture, and here you can see water, ashes, and organic fraction. In general, we hope that the main part of biomass is organic fraction, since we need this part to our energy processes, but water could also have very high percentage in biomass. And on the right side, you can see also a terminology we use to indicate, to show our energy parameters. Okay, so for example, when we will talk about energy content in biomass, we can talk about the sample as received. This is the English way to indicate, to show this biomass. And as received means that we are talking about energy content of biomass in its totality, in its complex. So considering organic fraction, ashes, and water. But we can also refer the energy parameters to dry fraction of biomass. So we are considering only ashes and organic fraction. So we have, in some way, we eliminated the water. So we can refer energy content only to dry matter, dry fraction, or we can consider only the organic fraction, and so we can consider the parameter refer to dry ash-free basic. So the biomass without water and without ashes, dry ash-free basis, DAFB. This is the English acronym. And here, you can find the basis we can consider when we talk about biomass parameters. And it's very important because the same parameter, energy content, can change in a big way if we are considering wet basis, dry basis, or dry ash-free basis. So it's important to know what basis we are considering. Okay, and this is valid for all the parameters we will consider. Another, here you can see some information about the volume the biomass occupy in the space. It's a very important parameter because when we talk about energy, bioenergy processes, we have to consider that we need a store for this biomass. And since we can have wood, but we can also consider chips or pellet, we have to know how many kilograms, how many tons can stay in 1 cubic meter, okay? Because, of course, yes, you can see this wood is distributed. So you don't have the possibility to have all space available for biomass, but of course, when you put biomass into a store, you can also have some empty parts where there is air. Okay, it's okay, and so it's important to know this parameter, and usually this parameter is called a cubic meter, stereo cubic meter. It's a particular unit we use to indicate how much biomass can stay in a cubic meter. So stereo cubic meter. For example, in one cubic meter, we can have, for example, 600 kilograms of wood. Okay, so in 1 cubic meter, we can have up to 600 kilograms. For example, we can have also 8 kilograms pellet, but only 200 or 300 kilograms chips, and this is due to the, of course, to the space, to the empty parts we have when we store several kind of biomass, and it's very important to also to know this parameter. Okay, then now I will have a very quick overview of these parameters because we will see the Biomass Research Center laboratories, and of course we will have a look to the one of these laboratories, which is the part where we characterize the biomass. So I show you, of course, in this presentation, in these slides, but we also have the possibility to look directly these laboratories and also how we can make this characterization. In general, you can see the most important parameters for biomass that are shown here. And for example, we just introduced moisture, okay, so water content or ashes content, so how many inorganic matter is present in a biomass. Also, we will talk about volatile substances, which are in the main part the organic fraction, the specific content of carbon, hydrogen, and nitrogen, the energy content, the heating value, okay, and for example, for pellet, the mechanical durability, which is another parameter used. Of course, also macro and micro elements like metals or chlorine or sulfur, and also the fusion temperature of ash. which is another parameter important for some applications. This is the machines, the analysis machines we have in the CRB laboratory. So we have a mill for the preparation of the biomass samples. We have a thermogravimetric analyzer to measure moisture, ashes, and volatile matters. We have the calorimeter for the measure of heating value, low and high heating value. The analyzer for carbon, hydrogen, and nitrogen elements, the pellet durability, and also it's only one, but we have several chromatographs, ionic or also liquid chromatographs to analyze the content of chlorine, sulfur, and also a lot of other elements and composts interesting for some bioenergy pathways. I go very quickly, like I said you, so I don't read the law to measure humidity and so. So starting from the thermogravimetric analyzer, I just say you that it's like a balance. So we measure the weight, we put biomass with an increase in temperature, and so when we are over 100 degrees, so for example 105 degrees, 110 degrees, we have the water evaporation. So we measure the difference of weight, and we automatically know what is the water content, what was the water content in biomass. Then we make a sort of combustion and weighing the weight of biomass after the combustion, after the high temperature. We measure the ashes content, and then with the difference we can also define the volatile substance content. So I jump the equations to know these parameters. So it's a very simple process where we use different temperature to measure the free parts we can define into the system. Here are some pictures, but of course we can have a look during our last lesson, the fourth lesson we will have directly into Biomass Research Center laboratories. Okay, just a moment to show you this important picture, this important graph, where you can see the energy content in vertical and the moisture in here. So this line show how, of course we can imagine it, but how the energy content change with moisture. Of course, if moisture increase, the energy content decrease, and we have a direct ratio between energy content and moisture. And for example, you can see that pellet, which is a very dry biofuel, usually the moisture content is under 10%, has the highest energy content, okay, expressed in kilowatt-hour per kilogram. For example, wood can have a water content of 20–30%, of course, and so the energy content decreases. And for example, wood chips, fresh wood chips, usually have a very high water content, very close to 50%. So half biomass is water and half biomass is solid biomass. And of course, the energy content is very low. For example, is less than half compared to pellet, for example, or also to wood. So this is the difference between different biofuels. Water content is a main parameter to know what is the energy content. And in some cases, it's necessary to dry biomass. Otherwise, is not useful for some energy processes. So we have to reduce the water content to make this biofuel useful for some kind of energy process. Okay. Another parameter is ashes content, and also this parameter is important and very variable in several biomasses. Here you can see that, for example, rice, the rice cover is quite a large part is ashes, 20%. But for example, some forestry trees has a low content of ashes, lower than 1%. For example, straw has a very high ash content, close to 9%, also cereals. So this is another parameter, important parameter, because of course, these parts it's not used into the energy process, and also it's a residue you have to consider at the end of the process. So if you have 10% of ashes, it means that at the end of the process you have 10% residues. And so you have to know, because you have a cost for moving this residue to waste pathway, or to for example to recycle it, but it's a cost inside this in general inside the process. Okay, I go very quickly without deepen the process you have to do to use this machine, just to see what is the result of the analyzer. And here you can see, for example, in the blue line, the weight, okay, the biomass weight, and on the left side, on the right side, you see the temperature. So you can see that we start from this part, because we are talking about weight loss. So you start from here. For example, here is the water content, because you are in the range between 100 and 200 degrees. So the weight loss is moisture. Then you move to another temperature, and here you have the volatile substance when you move to 800 degrees, and then you also make the final combustion more than 900 degrees, and the remaining weight is only ashes, and so you can have the information about, yes, moisture, for example, 10%, volatile matter 80%, and for example ashes around 1%. Okay. Very quickly, another instrument you can use to measure some elements: carbon, hydrogen, and nitrogen. These are the three main elements you find into a biomass. So the largest part of biomass consists of carbon, hydrogen, and nitrogen. Then you can have some oxygen, for example, and of course sulfur, chlorine, and metals, but these are in a very smaller percentage. And you have a system that burn the biomass and read the generated gases from biomass, and so the system evaluates the nitrogen, carbon, and hydrogen content in the biomass. Another, maybe the most important parameter is the energy content, the high heating value, and this is HHV in English, and the low heating value, LHV in English. And of course, these are two ways to evaluate the energy content of biomass, and of course the difference is connected to moisture. Okay, so low heating value is a higher energy content that don't consider that water when we have the evaporation of water, we put away energy from the system, and so if you consider this step, if you consider you have a loss of energy, you have to consider low heating value, which is a lower energy content that consider this problem. Okay. And we have a system that is the Mahler bomb is called. You put some biomass inside these systems, which is full of oxygen, and there is a part here where there is some water. Okay, is covered by a strait of water. Okay, then this is there is a combustion here when the process starts, so there is something like an explosion. Okay, so biomass burn produce heat, and so the water temperature here increases, and yes, evaluating this increase of temperature, we can evaluate the energy content of biomass. Okay, so these are some way to see. Here there is water. Okay, so this is the bomb, the Mahler bomb. This is the part where there is water. Okay, so when the combustion, the explosion is here, this system exchange heat with water that increase its temperature, and the thermometer can evaluate this increase and show you what is the energy content following this very simple equation. This is another way to evaluate, taking consideration some parameter inside the instrument. Okay. Okay, here are some information about low eating content of some biofuels and also some fossil fuels. You can see, for example, wood, which has a low eating value between 2,500 and 4,500 kilocalories per kilogram. And here you can also find the equivalence with other unit measures. For example, wood has an energy content, low eating value between 3 and 5 kilowatt hour per kilogram. For example, compared to fossil fuels, of course, this energy content is lower. For example, diesel has an energy content in approximately 10,000 kilocalories per kilograms. The same for gasoline. Methane has a low eating value of 8,000 approximately kilocalories per kilogram, or kilocalories per cubic meter in this case. So an important information you have to know when you consider biofuels, biomass, bioprocesses is that, of course, and I have to say, of course, the energy content of biomass is in the largest cases lower and very, very lower than fossil fuels. Fossil fuels energy content. This is a well-known limit, but we can consider bioenergy pathways knowing this limit. Okay, chlorine and sulfur content, we use chromatography, so I don't have time to to speak about the chromatography systems, but just to know that it's a very, very important part of chemical analysis world that allow to measure a very, very big families of elements and components. And so we can have liquid chromatography, ionic chromatography, and it's based on some columns where the samples moves, and these columns make the sample separate into the main components, and evaluating the time every component needs to reach the end of the system. You can evaluate what component is and what's its content in percentage, for example. So in 1 minute I talked about chromatography, but of course we don't have time. But here the sense of these analysis systems. If a sample consists of two composts, two elements, when it moves along the column, these two components have an affinity, a separate affinities with the substances we have inside the column, so they move with different speeds, and so they arrive at the end of the column in several times, and you can see the chromatogram. And here I can see, okay, element A is, for example, glucose, and element B is xylose, for example. Yes, this area show me the percentage of each compost. So I go very quickly. Also, the pellet durability is another parameter we use to know how many resistance have pellet to the transport step. And so it's important because pellet are small cylinders, okay, where sawdust is pressed. Okay, and when you move during transport pellet, you can also obtain again sawdust, and it's not useful for example, your boiler or your fireplace or something like that. So the durability say how much of pellet remains in good composition. For example, 97%. It means that 3% is you could lost it because it's again sawdust, so you could lost it. Okay, I complete this this topic. So the chemical physical characterization, having a look to two very different biomass, just to appreciate how much these parameters can change in a biomass compared to another biomass. For example, we will compare wine prunings, so some lignocellulosic biomass you have from the pruning of viticulture for wine production, and here you can see a picture, and we will compare it with pellet, for example, that you obtain from sawdust from forestry maintenance. So different biomass, but not so different, because you should mind that we can also have manures, for example, or very liquid biomass, for example, vegetable oil. So we are comparing two different biomass, but not so different, and you can see how much some parameters change. For example, regarding vineyard pruning, the moisture content is very high, 41%. Ashes are 2.5%, and of course the volatile substances are the main part, because of course we are also considering we are excluding water. We are considering dry bases, so you can see that water is not considered here. Okay, it's apart. Fixed carbon is the only part of carbon you can find into biomass. The high and low heating value expressed in megajoule per kilogram dry basis, 19 and 17 megajoule per kilogram dry basis, and the carbon content. You can see that it's the main part of biomass. It's very close to 50%. Then, of course, hydrogen, which is about 8%, nitrogen. Of course, we have oxygen, chlorine, sulfur, and so on. And we can compare this information with pellet. And here you can see that the main difference is moisture. I I just gave you this information. Here you have a very low moisture, approximately 7%. A very low ashes content, 0.20% approximately. And of course, this means a higher energy content. You can see that we are approximately 20 megajoule per kilogram dry basis, and the low heating value is 18.6 megajoule per kilogram. Okay, and also the carbon content is higher. We are more than 50%, 51%. Hydrogen content 60%. Nitrogen very low. So you can see that there is a very large difference between biomass. I just told you about, for example, manure. This is a completely different biomass, where water is the main part. Usually 60–70% of manure is water, for example. There is a higher content of nitrogen, a very low content of carbon. And why we have to know these parameters? Because, and this is probably the most important slide we will talk about. So why it's so important to know the composition of biomass? Of course, because this composition gives me the information I need to make a choice of what process I can do, what process I can perform with this kind of biomass. And so this make me introduce the next topic of this lecture, this course, which is the bioenergy conversion processes. So we talked about biomass typologies. We talked about how to transform biomass into biofuel. Then we can now talk about I can, from a biomass, from a biofuel, move toward a process to a finally bioproduct. And this finally bioproduct could be energy, of course, and is the very important part of this world. Through a particular process, I can produce energy, electricity, heat, and cool energy. But also I can produce, for example, biofuels, biodiesel, biomethane, bioethanol in substitution of gasoline, biohydrogen, which is a quite new energy vector we are exploring into research and also into some development systems, or for example bioplastics, biolubricant, and so on. I can continue for all the morning showing you some final bioproducts you can obtain. Okay, every kind of bioproduct must follow an energy process and an energy pathway. Okay, and of course the first element you have to consider is the composition of biomass, is what parameters are, what are the main parameters in the biomass you are considering. Okay, and so we can start to introduce this family. Of course, there are not all the possibilities you have, but in general, the large part of your pathways follows one of these processes, or probably follows a combination of these processes. So this is the basis of quite every bioenergy process. Okay, and you can see two or better three main families of energy conversion processes: thermochemical processes, biological processes, and I can say mechanical processes. Okay, and of course we will have a look to every of these processes. Just to introduce them, you can see that we have three typologies of thermochemical processes. Probably you should know the combustion process, which is the basis of probably 95% of every process, of every energy process, because you have combustion in your boiler to produce heat for your house. We have combustion processes for produce electricity at industrial level. We have combustion processes in quite every engine for our cars or every transport system. So it's the most common thermochemical process. And also gasification and pyrolysis are two other processes we will talk about. Okay, you can see these two elements here. What does they mean? M percentage is moisture. Water content we have introduced a few minutes ago. So if biomass has a moisture lower than 50%, probably you have, of course, you have to move towards thermochemical processes. And of course is the consequence of energy content. If you have too much water, you have a low energy content, and so it's not useful to use a thermochemical process that in general needs energies from biomass. Okay, the second parameter is the carbon-nitrogen ratio. So what is the content of carbon compared to nitrogen? And if you have this ratio higher than 30, probably you have to move to thermochemical processes, because of course carbon is the main element that produce energy in a thermochemical process, and so if you have a high value compared to nitrogen, you have to move to thermochemical processes. The second family of bioenergy processes is biological processes or biochemical processes. This is a category where you usually use some kind of microorganisms that do the work into the pathway. And before going to the processes, to the specific processes, just a look to the biomass parameters. Here you can see we have the opposite parameters. The biomass useful for this biological processes usually have more than 50% moisture, so a very, very high water content, and also a carbon-nitrogen ratio lower than 30, so less carbon content and higher nitrogen content. And of course, the reason of your choice is that when we work with the microorganisms, you also need you need the carbon source, of course, but you also need the nitrogen source and also water in general source to yes, to perform your biological processes. So you can see in this picture how the previous part is connected to this part and to the following parts of the course. Okay, and then we will have a look to some biological processes. For example, we will have a look to fermentation, where you can use sugar crops, amidaceous crops, and also lignocellulosic residues. Okay, and here the previous lessons information are very useful, because here you can see that you, for example, need cereals, or for example sugar cane, but also lignocellulosic residues from agriculture, forestry, agroindustry, and so on. And for example, fermentation is used for bioethanol production or other biochemicals production. The other very interesting process we will have a more important look is anaerobic digestion, that usually needs, for example, manure from animals, or very fresh vegetables. And of course, these two processes are different also into the not ever, but the microorganisms used are different. For example, the fermentation is typical of yeast, lieviti in Italian, yeast. The anaerobic digestion is typical for some bacteria, but it's a very general definition, and we have also particular cases, so it's not a law, okay? And this is another very important family. Then there is also another families, but it's very different with these other two families, which is mechanical processes. Mechanical processes means, for example, the transformation of biomass into biofuels. For example, when I need wood chips, I need to cut, for example, trees or branches or residues. Okay, and this is a mechanical process. Or, for example, the extraction of vegetable oil. You usually have some seeds that you have to press with a mechanical press, and you extract oil. It's a mechanical process, okay? And so it's a third family that is particular for some biomass. So it's not so useful to show this parameter, because these are typical parameters of some particular biomass. So you don't have to make a choice like here, when you have to make a choice between thermochemical or biological. You have, for example, vegetable oil, and vegetable oil has a moisture of 35% and a carbon nitrogen ratio of approximately 35 or more than 35. Okay. Just to make a zoom to thermochemical processes, which is the first family we will treat today. Here you can see a more detailed informations. Okay, we just said that we have 3 different processes we can we have available three main processes, okay? So we can also add other processes, but for example, are very similar to pyrolysis or less used processes. Main processes are combustion, and here you can see two important informations. Here are it means equivalent ratio. It's the quantity of oxygen you need to make useful the process, and usually you use a lot of oxygen, more than the stoichiometric one you need for the combustion reaction. Okay, so you are sure you are you are obtaining a complete combustion. So you usually introduce a lot of oxygen. In general, you introduce air where 21% is oxygen. So you introduce a lot of air, more than the stoichiometric one requested, so to have a complete combustion. This process has a very high temperature, which can reach also 1,800 degrees centigrade, and the goal of this process is to produce energy. So this high temperature is energy, is heat that you can use for your purposes. Produce electricity, make your car move, produce steam, and so on. And here the combustion products. Okay, so at the end of the combustion, from biomass you have energy, of course, and CO2. Of course, every process produces carbon dioxide. Water, better to say steam, because we are considering very high temperature, and ashes, which is the parameter you should know and you obtain at the end of the process. Okay, so this is the well-known process you should just know, of course. The second process is gasification. The difference is here. You can see that the equivalent ratio is 0.25. So we introduce 25% of stoichiometric oxygen you need for your combustion. So it's not a combustion, but it's a gasification. So the oxygen, the low oxygen needs to have a combustion to produce energy for the process. But the gasification, which involves the large part of biomass, is a process with lower temperature, you can see, and the goal of this process is not to produce heat directly, but to produce a sort of gaseous biofuel. Okay, here you can see that the final products are CO2, of course, water and ashes, but also a gas. So the goal of gasification is not to produce directly energy, heat, but to obtain a gas. For example, we talk about syngas, which is a gaseous biofuels that you can use in another process to produce energy, to make some system moves and so on. Okay, so it's the goal is different. The scope is different. Okay. Please stop me if something's not clear, of course. I said you last lesson, and it's valid till the end of the course. The third process is pyrolysis, and is another possible process, and you can see here the equivalent ratio is 0. So we don't use oxygen, we don't introduce air and oxygen. We only treat biomass with a temperature of, for example, 100 degrees. And the result is that you obtain, of course, some water, some ashes, but the goal in this case is to obtain free bioproducts, which is a gas here also. So something like syngas, we can call it pyrogas to make difference with these two gaseous biofuels. You obtain also a char, which is a solid biofuel, char, and also a liquid biofuel. It's an oil, okay? So the goal of this process is to transform biomass and to separate it into three biofuels: a gaseous biofuel, a liquid biofuel, and a solid biofuel, okay? Is clear this part, because it's fundamental. From now we will have a look to possible process systems, but it's fundamental to have in mind this classification of processes: thermochemical, biological, and mechanical processes, to know that every biomass in general has a typical pathway, not ever, of course, but in general as a typical pathway. And of course, every process moves towards a final specific bioproduct, and we started to see it into thermochemical processes, where you select the process in function of your final bioproduct you want to obtain. The combustion produces directly energy in the shape of heat. Gasification produce a syngas, like a gaseous biofuel, and pyrolysis produce free biofuels, a solid, a liquid, and a gaseous biofuel. Okay, we start from combustion, just to introduce what we intend with combustion. We just introduced it, but in general, the combustion is an oxidation okay, where you have a biomass, or in general a fuel, and oxygen, and of course some heat to make the reaction start, and then we have the combustion reaction. And here you can see the typical reaction of the main elements in biomass. Probably the third and the fourth equation are typical for biomass, when you have carbon, hydrogen, oxygen, some chlorine, of course nitrogen in a very, very low part, because you must remember that the nitrogen content in this biomass is very low. So these are the reaction. So you can see that biomass, or this one or this one, reacts with oxygen, and the results are carbon dioxide, vapor, and heat. This is the decidured final product for this process. Then you can use it in a lot of other processes, okay? If you have chlorine, you must have in mind that you could obtain some pollutants, and also nitrogen and sulfur can produce some oxides, for example, nitrogen oxides or sulfur oxides. Okay. Another important information you should know when you talk about biomass combustion, so we are focusing on biomass combustion, is that you should take in mind that, for example, comparing to methane, we have a biofuel with a volume. Okay, think about wood, for example, or pellet or chips. We had a biofuel with a volume. Okay, so in general we have three phases during the biomass combustion. A first drying phase where we are more than 500 degrees, and so water inside the biomass starts to evaporate. Okay, and this is the first part. We have a second part, which is a sort of pyrolysis. Okay, so we are talking about combustion, but we have a sort of pyrolysis. Why? Because when the temperatures start to become very, very high, 300, 400, 500 degrees, we have this situation that inside the biomass we have very, very high temperature, but there is no oxygen because oxygen is around the biomass. So here we don't have oxygen, the famous equivalent ratio is 0, and so we are a sort of pyrolysis where biomass start to transforms into char, for example, solid char, or into gas, and you can see that this gas exit from the biomass. And finally, we have the oxidation, the final oxidation. So when the oxygen meets biomass, so in the surface, or also when it reach the internal part of biomass, we have oxidation, and here we have energy production, and you can see the flame that take the combustion phase. Okay, so we have these three phases. Of course, methane combustion is very different because we have only the oxidation phase. Methane is a gaseous fuel, so it has a very, very easy mixing with air, with oxygen, and so the combustion is very, very easy, and the oxidation is the only phase we have. Here you can see a more precise list of steps you have during the combustion. So this is the biomass. You can also see the composition of biomass. Here you can see this information of biomass. Every one carbon atoms in biomass in general corresponds to 1.5 hydrogen atoms and 0.7 oxygen atoms. So biomass, we have the first part that needs it, which is the drying phase, where water goes into atmosphere. Then here we have the pyrolysis phase, so we produce some kind of char, and here you can see the composition of char, some carbon monoxide, because we don't have a perfect combustion, so we can obtain also carbon monoxide, hydrogen, and so on. So some gases and some char, and finally the oxidation, and so we have the final production of CO2, NOx, H2, and of course energy, which is the main goal of combustion, and ashes like a residue of the process. It's okay? Okay, now as usually I move towards interesting combustion systems. So how we can use these combustion processes. So what is the combustion system we can use? And yes, you can see, I go very quickly. Okay, sorry, just a stop to what I was saying, to have a look to the biofuels. I don't know if I shown you this picture, but just to understand what are we speaking about. This is pellet, you should know, small cylinders. These are wood chips, so small pieces of wood which have a low energy content, as you see, but also a very low cost, because you can obtain them from, for example, agricultural or forestry residues. Briquettes, not so used like biofuels, and of course wood, but wood is just for our houses. There are not industrial use of wood. When we talk about industry use of bioenergy, we talk in general about only wood chips. And so, biomass energy conversion systems start from your fireplace. It's the simplest ways to the most simple system for produce energy from biomass. But of course, we quickly move towards more interesting biomass systems. You can also see some other kind of stoves, wood stoves, pellet stoves, and now we can move to boiler system. So to biomass systems that produce heat for our heating distribution system. In general, the boiler produces heat that is exchanged with water, and so you obtain hot water that is used, for example, in your terminals to produce heat for your rooms, for also for your shower, and so on. Okay, and here you can see, I don't know if I have other yes, no, I don't have other pictures here, but you can see another typical way of biomass combustion. In general, you have a first combustion where you have the combustion of wood, and then a secondary combustion here where gases produced from the first combustion are burnt, because yes, you as you see in the process, you produce also some some gaseous biofuels, and you also have to burn them to maximize the energy production. So you have two separate combustion phases, primary and secondary combustion, and yes, here you can see the heat exchanger where exhausted gas transfer heat to water, for example, and then water reaches the heating system in your room, the heating system of an industry, the heating system of a commercial shop, and so on. So this is applicable to every size. So from the typical size of an house to an industrial size for large quantity of energy production. Okay, just very quickly to zoom only to important information. Okay, these pictures let me speak about another topic we just introduced. One of the main differences between, for example, methane boilers and biomass boilers is the store system. We just introduced this theme. You usually don't have to think about the gas the boiler needs, because you have a pipeline that is connected to your methane boiler, and yes, if Russia don't close the pipe, we should have every available gas into our boiler. If you have a biomass boiler, you also have to think about the biomass supply to the boiler, and also the biomass store to the boiler. Otherwise, you have to stay all the day to charge the biomass. So you have to also to plan, to design a store that automatically, like you see here, automatically moves the biofuel to the boiler. Okay, and for example, it's a small boiler for your house, but if you have an industrial energy system, you have a very big store that can the boiler be automatized for a large time. Okay, so you can see some store system. I'm moving towards higher size biomass boiler. For example, you can see here we have a store which has a size of a room. So if you want to use wood chips boiler, you need a very large store, and so it's not convenient in small houses. Okay, so we just are talking about big houses where this kind of space for the boiler and also for the store is available. And here you can see that when you have the store full, here the system is completely automatized. So there is a system that moves wood chips here, then a cochlea, then moves the chips here, and finally cochlea that charge wood chips into the boiler. So we have, of course, the possibility to have an automatic system, but of course you have to supply this store every 2 months, 3 months, every year. It depends on the size, on the dimension of the store. Okay. So we are quickly moving towards larger plant, industrial plant. You can see, for example, this kind of biomass boiler with moving rate, ovvero griglia mobile inclinata, lo vedete in italiano, moving rate, and it's typical of large boilers, very large boiler for industrial application. So you charge, you move wood chips here, and this is the boiler where biomass, yes, goes down into this moving rate. Oxygen, primary oxygen, enter from here and make the first part of combustion. Okay, and then some gaseous biofuels continue the combustion here. You can see a ventilator for introducing other oxygen here and here to complete the combustion. And then here the exhausted gas transfer heat to, for example, water or other thermofluidodynamic liquid. Okay. Also, for example, organic oil is used, or also steam to produce electricity. So we have moved towards more industrial systems. Okay. Just to give you some other input about biomass systems, just this information. Here you can see a very simple system, biomass boiler system. So you here have the production of heat, exhausted gas transfer heat to water, for example, and then you distribute the hot water to your heating system, and a pump make this water circulate and receive it from the boiler. I give you the information about this, which is another important difference between biomass boiler and traditional methane boiler. Biomass boiler are very low system. So what does it mean? You need some time, and you need, yes, in general, a lot of time compared to methane boiler to reach your desired condition, final condition. So you have to start with the increasing of temperature. So the biomass boiler starts to burn biomass. The temperature rise slowly. So you have a drying stage, you have pyrolysis stage. So you need, in general, some hours, 1, 2, 3 hours to reach the desired condition. And so if you don't want to wait hours to have heat into your room, but also into your industrial production, you need a store of hot water. So you can store some hot water that you can use when you have to wait the boiler is ready to work at its power. Okay, and of course you can use this store system when you switch off the boiler, because you have the same problem. When you switch off the boiler, for some hours the system continues to produce heat, because you need to wait that the combustion decrease temperature. And so you can use this energy, storing it here, to use when you restart the day after, or in another moment you have to restart with your biomass. So it's just another input that is specific for biomass boilers. Yes, I go very quickly just to see some pictures about wood stores or for example, in general, if I have more time in the course, we make also some examples of the the designing, the evaluation of the volume of a store for pellet, for wood chips, and so on. But of course, we don't have time now, because otherwise we have to stop the course with these exercises. So I go very quickly here. Some moving systems. We can use also some bags for pellet store. Of course, some from some stores for wood chips. A lot of possibility. Of course, you can have a specific building in this case for the energy system. So we are not speaking about your or my house, but if we speak about a very important house, or for example other users like industrial areas or commercial areas, or an hospital, for example, so very large building, we can think about this this building for boiler and for the store, and so a lot of possibilities. So this is the easier part, because you can see you can create a store underground, and also use an underground of your building, and yes, you can easily charge the store, and don't need so much space to have these systems working. Okay. Or another possibility is this one, or a container. There are many possibilities. Of course, as I said to you, we are moving towards bigger plants. Here some storing and moving system. I just told you about the cochlea, to move wood chips and to charge it into a boiler. Some kinds of other systems to move inside a store the biomass, a conveyor belt, for example, or some racks, moving racks. Okay. Other kind of moving systems to move biomass. And of course, we have reached the very big size. Here you can see that trucks moves wood chips. Here then there is an automatized store for the systems, and of course the production of very large quantities of heat. The combustion phases are the same: drying, pyrolysis, and oxidation and combustion. Also in your fireplace, and into both into your fireplace and into a big plant. Okay. Yes, these are other possibilities for these big plants with moving grate, with particular system. Here you can see the moving grate, and these points are where hail enter and meet biomass and allow the combustion into a moving grate. Okay, it's an internal view of the boiler. Other pictures of boilers with the heat exchanger for transfer heat from exhausted gas to water, for example. So a lot of technological systems to use biomass into these energy production systems. Okay, I go very quickly to this other very important concept, which is, okay, I just complete this slide or two, and we have a break, because I see that we are just 2 hours we are speaking. So when you move towards big plans, of course you have to consider that you have to maximize the energy production, and in general you are considering co-generation. So we are speaking about CHP plants, or combined heat and power production. So you have a biomass boiler that produce heat. You can convert this heat into electricity, for example, using vapor, or using air, hot air, or using other possibilities you have. And the final heat you can use, the final part of it you can use, you can recover it to, for example, make heating into an house, or into a lot of houses and buildings. We are speaking about very large plant, up to district heating. So the distribution of heat into towns, into industrial areas, into commercial areas. So we are district heating, teleriscaldamento. Okay, and of course, cogeneration has an advantage with separate production of electricity and heat. And here you can see what does it mean if you produce electricity in a separate system. For example, you can reach 36%. You can also reach 45% in some particular systems, but you have 50-60% of losses. If you have a cogeneration plant, you can reach, for example, 40% of electricity. You can also have 40%, maybe more, of heat to use into district heating or into heating systems, and only 10-15% of losses. So this is the added value of a co-generation plant. Then we can also speak about the 3 generation plants. The production of electricity, thermal energy, and cool energy for example, for summer conditioning, or for some industrial processes you may need cool water. Okay, and of course you have an energy added value we have just appreciated, and of course an economic. It becomes an economic added value because you have again, you need less feedstock, and so it's a lower cost. And of course, an environmental added value, because you produce less pollutants, less CO2, carbon dioxide, than separate processes. So 3 kind of added value: energetic, environmental, and economical added values. Okay. Of course, we have also to consider the weakness of cogeneration. So you can use combined heat and electricity production if you have the possibility to use it in the neighbors. Okay. Of course, electricity could be used also very, very far away from the production point, because we have a distribution of electricity that cover all over the world, but you don't have the possibility to transport it in a long way. So you have the availability, local availability of it, of it use. Okay, and so this is a weakness, but of course it's not a weakness if you realize this kind of plants near some heat and cool users. Okay, of course I will not speak about engines, turbines, Rankine cycle, diesel or gasoline cycle, because it's you should just have this this information known from your university studies, just to show you where combustion process also for biomass can reach. And we can also reach turbines, diesel engines, for example, fed by biodiesel, gas turbine fed by biomethane. So combustion can reach a lot of potential applications. Okay. Also, cogeneration could be used in a small size, so for local buildings or for local areas. The progress of technology allows to decrease the size of these cogeneration systems. Some information about these systems. Just a mention to organic Rankine cycle, which is a particular biomass systems, because it's a technology used quite also into biomass systems. It's quite different between organic Rankine cycle, with traditional Rankine cycle. Traditional Rankine cycle is the thermochemical, the thermofluidodynamic fluid, the thermal fluid, is water. No, you studied a Rankine cycle with water and its evaporation to produce energy. The organic Rankine cycle use an organic fluid, and so it's different with the Rankine cycle. It's the same with the system, because we have an evaporator, a generator, a condenser, and a turbine. But of course, change the fluid, and so the temperature, pressure, and other parameters changes. I don't want to go in deep with this, but just to note this kind of organic Rankine cycle systems allow to produce electricity with an efficiency of 18 up to 24%. So not so high efficiency, electric efficiency, but you can use a very, very large part of it, up to 80%, which with only 2-3% of losses. So it's a very interesting system for application with district heating. So you produce electricity, and you also have district heating fed by this part of energy for energy use, and so your energy efficiencies is very, very high, and you have a very, very low losses. And here you can see the system, for example, the automatic system for wood chips store, the moving system that charge chips into the boiler. Okay, here we produce electricity that reach every part of the world, because you can transport electricity. You recover sorry, here the production of electricity, and here you recover a large part of hot water that can feed district heating. And here, for example, the ashes you store into some system, and then the trucks transport them to the waste systems or to the recycled system. Okay, so this is a picture that shows this characteristic and this some chemical characteristic. And of course, it can also be used for produce cool water for cooling systems, and so you can use also it in summer. So district heating can also be used in summer for cooling system supply, and so the energy recover is much higher, because you recover heat not only in winter or autumn, but also in summer. And here some information about district heating. Okay. So
is it possible to make some questions? Is it possible to make some questions?
Of course. Sorry, I didn't ask you if anyone has some question. Of course, please.
Thank you so much. Thank you so much. Could we go to page number 192?
Of course. You. 192. My very, very short presentation. Okay. So.
Okay, I wonder which technologies between these you showed into this slide is quite mature, and if there are existing.
Sorry, what technology?
What is the technology more matura? La tecnologia più matura tra queste, se ci sono degli impianti esistenti che vengono utilizzati, usati attualmente? Questa sarebbe la prima domanda.
Okay, I can answer the first question. Okay, I think that of course combustion plants are very, very mature. The use of biomass for boiler or co-generators is very mature. I'm studying these pathways for 15 years, but of course these technologies are available for 20-25 years. So combustion, of course. Also, anaerobic digestion is a very mature technology. 20-25 years we have just plants working in Italy, of course, but also in the rest of Europe and all over the world. Gasification and pyrolysis are quite new technologies. There are, of course, plants working with these technologies, but of course, the technology is still new, and in some cases still needs to improve the efficiency, improve the durability of these plants. So gasification and pyrolysis are the less mature technologies. But in Italy we have I have not shown you the specific slides with regional plants, but there are a lot of digester plants near Rome, of course, in Umbria, and in the rest of Italy. There are a lot of plants, combustion plants. And yes, also gasification plants are present in all of Italy. We have a plant near Perugia, very close to our university, a small plant, and there are a lot of plants. Yes, gasification and pyrolysis probably are the less mature technologies. If I answered your question, you can make me the second.
Could I go on? I just got another question, little question. For example, is actually biodigestive, anaerobic biodigestive plant actually installed in Italy? Are they used for the cogeneration, so for the production of energy, electric energy as well?
The answer is definitely yes. These plants are often used for cogeneration. So the main goal is to produce electricity, of course, but they for example, for digester plants, and I think we will have a look now in anaerobic digestion plant. You have to use some heat for the process to maintain the temperature in the grid reactor you have for the anaerobic digestion. And a lot of plants also use the rest of the heat you have available for the heating system and so on. I lost another. There was another question or part of the question. What was? Are available. Of course, these plants are of course available. I know, for example, only in my region in Umbria, I can say that we have at least, I know, 7 or 8 plants only in Umbria, but maybe we have more plants, more digestive plants, and of course near Rome, I think there are a lot of these systems. These systems are very interesting also because some of these plants that produce biogas and biogas is used for energy production, actually they are moving towards biomethane production. So they don't produce directly energy, but they use biomethane to separate biogas to separate biomethane, and so separate CO2 from biomethane, and biomethane could be used for energy purposes or also for the transport sector, for traditional methane car that can be fed by biomethane.
And is it possible to use the biodegradable part of urban waste for biodigestive, anaerobic biodigestive plants?
Of course, absolutely. It's clear that you have some authorization to obtain that are quite different from only biomass, because you are using organic fraction, but of course you can use, and it's probably the best use of organic waste, the organic fraction of waste.
So is it considered as a renewable plant, even in this case? Yes.
If you use only the fraction, the organic fraction of urban wastes, yes, of course.
Last question, if possible. I cannot. I don't want to.
You are welcome.
Okay, thank you so much. Which are the typical sites of these plants?
Yes. There are 2 typical sites, and the reason is probably an economical reason. The typical size are 200 kilowatt electric kilowatt and 1 megawatt, so 1000 kilowatt. Probably the most used size is 200 kilowatt, and the reason is yes, the incentives that are higher for small plants, and also the authorization process that is easier for small plants.
So it's for
to have plants higher than 1 megawatt is not so sustainable, because you need a lot of biomass, so you need to supply biomass from also long distances, so it's not so sustainable.
So I see. So they are mostly used as a little plants, not so big, 200 kilowatts. And
yeah.
very last question is, which are the typical problems? Which are the typical problems of biodigesters, anaerobic biodigesters?
Okay. Of course, smells.
Okay.
Yes. A general problem for biomass plant, which is the social acceptance of these plants. So people around these plants, I don't know people around these plants who are happy to have these plants, but it's, yes, I just talked about it the last lesson. There is also a NIMBY syndrome, so not in my backyard. Of course, in the past, we have also bad examples of biomass plants, and so people fear about the possibility to use some strange feedstock. Okay, and so there are, I don't think there aren't other problems, because the turbine, the diesel engine you use is a traditional system that produces, of course, CO2, but it's normal in every process. So other pollutants are not present in important quantities. So smells and acceptance in general.
And is it possible to manage the smells?
Of course. It's not the object of my course, but my colleague Valentina Coccia also performed a course about the possibility to measure the smells and also to contain smells. So there are systems, there are biological filters that can control these emissions, kind of emissions. Not pollutants, but it's an emissions that create a problem to people close to the plant.
Thank you so much. Thank you.
You are welcome. You are welcome. Thank you for your very interesting questions. I move very quickly to. Okay, I think we were just here. Please let me know if you don't see the slide. So just to show you how the district heating works. So you have.
Sorry, but we can see the slides.
Okay, thank you very much.
I cannot see too.
Okay, thank you. So probably I didn't apri, open. Okay.
Will it be possible to have these slides whenever you?
Of course, I need to create a PDF file, because it's a huge presentation. But of course, I will provide you the PDF. If when the course finishes, if you still not receive the presentation, you can send me an email, and I will send you every of you the PDF of this presentation.
Thank you very much.
Okay, so if you now should see the presentation just to show you the district heating, where you have the only one energy production system that produce electricity in general and also heat, and of course a distribution to, you can see here are the single buildings you can reach with hot water, and also this hot water will be used in summer for cooling, for buildings cooling. You can have several possibilities to have this district heating, but it's only to know. Of course, the pipeline that can be run along also 5 or 10 kilometers must have a very, very good insulation. Otherwise, if you start with 90 degrees centigrade, you reach the last user with 20 degrees centigrade, and it's not useful for heating. So you have to use very performant pipes with very, very big insulation system. And this is the pipeline you have to create to reach the single buildings. And of course, then you have to connect with the building, which is in general an existing building. So you have to reach the building and connect to the heating system, to the local heating system. And this is a very important part, and not every house, every building have the possibility to connect with district heating. So you have to design with great attention this part. Okay, so a very, very quick zoom to gasification. Just to say something more, I have just told you. So gasification is a sort of combustion, but with less oxygen than the stoichiometric one you need. So the combustion, the small combustion needs to give to the system the energy the system needs, and while the gasification is the transformation of biomass into a syngas, okay, into a gas. And what this syngas consists of? The main components are carbon monoxide, which is a gaseous fuel, because carbon monoxide could burn to produce energy. Of course, methane, of course, hydrogen. So these are the main components of syngas, and it's the gasification goal. So to obtain a gas useful in other energy conversion system. So this is the difference with direct combustion. So in the combustion, you directly produce energy. You produce heat, and that heat is converted into energy. If you produce syngas, you can also use that gas into another energy conversion system, like turbine or engines, and you can't do this with combustion. So this is the difference. Okay, in the first way, you are using a solid biofuel, biomass, and so you can produce, of course, electricity, but with some particular cycles, like Rankine cycle or organic Rankine cycle. so with water or with, for example, organic liquid. If you obtain syngas, you can use it into turbine or engine. So that is the difference. And this difference also means a different energy production. I mean, you see that in combustion, the electricity in the cogeneration system, for example, you see, you have seen the electricity efficiency. The electricity efficiency is around 20%, while you maximize heat production, which is close to 80%. Okay. In gasification, in the gasification systems, using traditional turbine or engines, you can reach higher electricity efficiency, close to 40%, so 20% compared to 40%. Of course, you have a lower production of heat. So the choice of the technology depends also what you want to obtain. But of course, as I answered to your colleague, there are also some different with the progress of technology. Of course, combustion has a very, very great technology progress. Gasification still needs to improve this progress. Okay, so just to give you an overview of the process, I don't want to go on detail on the gasificator technologies and so on, because it's too heavy and we must touch a lot of topics, still touch a lot of topics, so I go quickly, but it's important to know some concept, and the one I said you. And so just to say that yes, to remark, sorry, to give you this information, the gasification work with lower temperature than combustion. Of course, you don't have a complete combustion, and you obtain a syngas. You can also obtain some other like pollutants, so liquid biofuels, particulate, acid gas. There are a lot of possible pollutants you can obtain, and of course you have to control these pollutants before they reach the atmosphere. The process needs some heat. This is the reason you use a part of biomass to produce flames, to produce combustion and give energy to the process. And you can use directly air, but you can use air to give the 0.5% of oxygen. You can use directly oxygen without air, without nitrogen, only oxygen. You can use also steam, and of course the low heating value of syngas increase. Here, using air, you have a syngas with a lot of nitrogen, which don't participate to any energy process. So you have the half part of syngas, which is nitrogen without energy content. So the energy content is quite low. If you use oxygen or steam, you have a very, very low presence of nitrogen, and so the low heating value increases, and is the double compared to the air one. Okay, so it's a difference, but of course air it's not a cost, oxygen is a cost to the system, so you have to evaluate it's economically feasible to use oxygen. Okay, so you can reach, as I said to you, 50% of efficiency, and the great part of this 50% is electricity. So it's very, very, yes, oriented to electricity production. So cogeneration is not so interesting for gasification. Of course, if you can, you should recover also heat. So, as I said to you, I don't treat this part of typologies of gasificators because it's too heavy and it's not convenient to stop here. Of course, I just give you an input about the syngas treatment. So syngas is a very complex mix of components. Of course, you need to use only components that participate to the combustion, to following combustion, and so you have to eliminate also the pollutants, and you can see particular some metals, nitrogen, tars, which is a liquid fraction that can move together the syngas, sulfur, chlorine, and so on. And so there are a lot of treatment systems to obtain a pure syngas with only the components you need for the combustion. And finally, for thermochemical processes, the pyrolysis process that is synthesized into this scheme, into this picture. The goal of the pyrolysis is to transform biomass using some heat. So, of course, you need heat to make this this transformation available. So you have biomass subjected to this range of temperatures. So from 400 degrees centigrade to 800 degrees centigrade, without any without oxygen. So in a atmosphere without oxygen. So the oxygen percentage is 0%. In these conditions, with these conditions, you can transform biomass with this high temperature into three elements: a solid biofuel, the char, a liquid biofuel, the tar, and a gaseous biofuel, which you can call syngas or pyrogas to make difference with gasification technologies. And then there are several typologies of technologies. I don't describe them, but just to say that the temperature in this range and the pressure also you select orients the final products to syngas, tar, or char. So you have to choose the correct conditions in function of your results in terms of bioproducts. And I can see also that, for example, syngas is of course a desiderated bioproduct because it's a gaseous biofuel that can be used like syngas from gasification into turbine or engines, diesel engines, for example. Char is a solid fraction that can be also used in some other energy processes. Probably tar is an undesiderated bioproduct because it's a liquid fraction. It's very, very dirty liquid fraction, which has great difficulty to be used for energy purposes. So it's not so desiderated. So you should try to maximize syngas and char production. And here you can see what is the main products you have when you move toward some temperature, and also the time you use the process. And so very flash processes, 1 second at high temperature to maximize gas, or very long processes to maximize liquid fraction if you want, or solid fraction. And just to complete this part, the low heating value, which is very variable into pyrogas, from 10 to 25 megajoule per kilogram. So it's probably the content it's higher than syngas obtained from gasification. And of course, we don't have nitrogen into the pyrogas, so the energy content increases. Okay, as the same as gasification, I don't show you the pyrolyzer, the pyrolysis systems. Just a final look to the emissions of thermochemical processes. It's another important topic you must consider when you enter into the bioenergy, bioproducts pathways. When you work with the thermochemical processes, you have some emissions that are mainly in the gaseous fraction, in the exhausted gases, but also, for example, in the ashes, so in the solid residue. In general, also comparing biomass processes with, for example, fossil fuel processes, you have these families of pollutants. The nitrogen oxides, the sulfur oxides, so the PM, the particulate matter that you have into the exhausted gas, and VOC, which are the organic carbon volatile substances, and are very dangerous for the human healthy. And these are the main pollutants. Of course, I'm not considering the carbon dioxide a pollutant, because you can consider the biomass as a zero balance CO2 emission. So the CO2, as we said in the first lesson, the CO2 emitted from biomass plant is the same the biomass stored during its growth. So in this way, you can consider that you don't have emission. But of course, every process we just see a few minutes ago produce carbon dioxide. But take in mind this consideration. Just to say you that from the Italian environmental law, every biomass plant, I just are talking about biomass plants, must control the emissions. And so in this table you can see that in function of the power of the plant, you must reduce the emissions under these values. So in every biomass plant, and mainly in thermochemicals processes plants, you need a treatment system, exhausted gas treatment system to to reduce the emissions and so to respect the low emissions. And so it's another very important part of the this great biomass sector to control, to correctly design the systems that reduce the emission in atmosphere. I go directly to pictures because it's just to show you how district heating is developed in Italy, and also not only district heating from methane, from fossil fuels, but also district heating from biomass is present in Italy. I don't want to say that this has a large diffusion because it's not true, but there are many examples of district heating from biomass, so from renewable energy. Also near Perugia there are some district heating, but we are talking about fossil fuel district heating, and also maybe they shouldn't work anymore. I know because the company had economical problems, and so they are not working. But near Perugia there were 5 or 6 district heating in the neighbors of Perugia, also close to San Mariano, which is very close to our university. Going quickly to the wood chips district heating, yes, there are some plants, not only in the north of Italy, near the Alps, where there is a large distribution of these plants, but also, for example, in Tuscany. In Tuscany, we have 3 district heating. We are near the mountains, where there is the availability of biomass from forestry, of course, and also the difficulty of traditional methane network to reach very isolated towns or villages. But so we have some kind of examples. And so you can see the biomass supply from forestry or from also agricultural residues, and the use of biomass into a biomass boiler. This is a moving rate. We just have a look when we were speaking about the theoretical part. Another example of district heating, just to note how the insulation is important. You see that it's a very large insulation system. Okay, to make you don't have so much losses during the length of the system of the pipeline. Sorry. The connection between the existing plants, the other important element I underlined, and of course a lot of biomass district heating in the north of Italy, in Trentino, for example. And here you can see also there is a very large size of these plants. Here you can see the wood chips stored open, and then a fraction of this biomass is moved to the biomass systems. But Yes, the overview is the same. You can see the boiler systems, the pipeline that reach also very far away buildings, and of course the process, the combustion process. Okay, in 2012, this municipality received recognition to be 100% renewable, and so they use district heating and also wood for local, for single-use user. Okay, this is the district heatings in Alto Adige, and 37 district heating fed by biomass. Okay, so there is a very large presence of biomass district heating in the north of Italy, and so other 30 plants. And of course, some plants are cogeneration plants, so they not only produce heat but also electricity. For example, the most famous is Tirano system that produce electricity and a huge part of thermal energy. And you can see also the extension of pipeline, 32 kilometers of pipelines, 700, more than 700 users, and other quality. I see, but there is a bad connection. Can you hear me? And could you see the percentage? Okay.
Yes.
Okay. I sometimes receive some message that there is low quality of network, but so I ask you. Okay. Other pictures of the pipeline, the realization. So it's, of course, it's not so easy to create a district heating in an existing town, because you can see you have to distribute the pipeline along street and along the quarters, the city, and so on. Of course, if you have a new town, a new quarter, you can design the district heating to, and so you can also realize the pipeline together with, for example, water or electricity lines or the other lines you need in every city. And these are some also picture of the characteristic of the distribution system. This is for example the district heating. You start here from 76 degrees and come back at 30 degrees. So you transfer heat to the user that, for example, produce heat, or for example, for shower or other uses of water. And of course, I don't have time to read everything, but of course, district heating means also a economic save, because the costs are lower than traditional heating systems. Okay, I go quickly with these pictures. This is an overview of the big plant. Of course, you have for example, wood. Then you have to chip. There is a chopper here that obtain wood chips. Then, of course, another store here covered by a roof to avoid rain that increase the moisture of wood chips. Here, of course, the boiler system and the electricity turbine, and of course from here start the district heating that reach all the buildings. Okay, in the very last part of this lesson, I will speak about only one of the biological or biochemical processes. So we now have moved to the second family of energy processes or biological processes, and we will speak about anaerobic digestion. I will speak about fermentation when, in the next lesson, we will talk about the biofuel production, because fermentation is a typical process not for directly energy production, but for biofuels production, and in particular bioethanol, for example, but not only, because also biodiesel could be produced in a particular way, or biohydrogen, for example. So today we speak about anaerobic digestion, and in the next lesson, when we speak about biofuels, we will speak about fermentation. Of course, when I was talking, I'm thinking about aerobic digestion. Aerobic digestion is another process, but for example, it's not used for energy production, but for example, for fertilizer production. So it's the difference is the presence or not of oxygen. Anaerobic digestion is a process in absence of oxygen. Aerobic digestion is in presence of oxygen, but it's a process used mainly for fertilizer production. Okay, so anaerobic digestion is a biological process. So every biological process use a typology of microorganisms. Microorganisms works for us because they eat the biomass we give them. They eat biomass, and they cut biomass into more simple components. Okay, so we start from a complex biomass. These families of microorganisms heat this biomass and produce other simple components. These simple components could be used for other microorganisms that eat them and produce another more simple component, and so on. So from biomass, at the end of the process, we obtain two main, very simple components. CO2, of course. We have carbon dioxide in every process, in every thermochemical or biological process, and methane. Biomethane, sorry, because it's a renewable methane. Okay, so at the end of the process, we obtain a gas, a biogas, that consists of two main components. Of course, there are also a lot of other components, but the 99% are methane and biomethane and carbon dioxide. Okay, so the purpose, the goal of the anaerobic digestion is to produce biogas. Then you can use biogas for the production of energy. In the most traditional pathway, you use biogas into a turbine or into an engine to produce electricity and heat Okay, so cogeneration system. And of course, the most interesting part of biogas is, of course, methane. CO2, carbon dioxide, is a component you obtain in the reaction, but for us, for our energy purposes, is not a feedstock, is a result of the process, but we don't use it, and it's yes, CO2 that goes in atmosphere. Yes, you can see it's very similar to the consideration we have at the beginning of the lesson. So when you have the as received biomass, this kind of biomass, the biomass you use for anaerobic digestion, a large part is water. Yes, you can see that you can have 10%, but also 98%. Of course, 98% is a huge quantity, not useful for energy purposes, but you can also have this composition. Of course, we are interested at the solid fraction, and in particular the organic fraction. And so you can see that ashes and also not degradable from microorganism part is not used. So we are interested only at this degradable part. Not degradable part, for example, is also in general cellulose. Cellulose is a polymer that bacteria used in these processes are not able to use. Okay, so this is the signification or the meaning of this undegradable part. Okay, so only a small part of biomass is used for anaerobic digestion process. And here, yes, a list of feedstock useful for anaerobic digestion. Of course, the manure from zootechnical companies, from cows, pigs, chickens, and so on. Of course, agro-industrial residues from beer production, from wine production, from fruit juice production, and so on. Also animal residues, of course, as we just talked about with Simona, the organic fraction of wastes is a feedstock for this kind of process. Of course, also other residues from agriculture, and of course also energy crops. I said this feedstock at last because they probably they are the best feedstock for anaerobic digestion. Cereals, sorghum, and so on are the best usable biomass, but with the problem we analyzed last lesson. So we have to use a food crop for energy purposes. We have to use agricultural lands for energy purposes. So it's a very interesting biomass, but with a lot of environmental problems. Okay, and so you can see it's the same cultivar like food agriculture, and so there is this competition that make this biomass not sustainable for energy purposes. So you can use them, but they are not sustainable, not so sustainable like residues, like manure, like wastes. Okay. I just focus on these graphs. Here you can see what does it mean that energy crops are better than other residues or menu. You can see here, for example, some cereals, for example, straw, or other plants have a biogas potential very, very high. So maize, you can see maize, straw, cereals as a biogas potential very, very high. Manure is interesting because you, in a circular economy way, you reuse these wastes, but you can see that they have a very low biogas potential. Of course, the cow or the pig hate this plant and used it for its purposes, and the residue of this cow, of this pig, has a low biogas potential. So this is the reason you can see this great difference. And the same difference is also for some agroindustrial or vegetable residue. They are all very, very low compared to energy crops. But of course, we should, we must, choose the residues when possible instead of energy crops. Don't have time to show you the costs. This is a way to maintain, I don't know the English translation of insilato di mais, but it's a way to to maintain the biomass for all the year, because when you collect maize or other cereals, you collect them into a precise period of the year, and then you have to use that biomass all over the year. And so the insilamento is a way to maintain, to avoid that biomass is not good because it's a fresh material, so could have some problems. Okay. And here you can see on detail the anaerobic digestion process. So this is the the picture we have just seen. So water is not used for microorganisms, the ashes are not used, the organic fraction in part is converted to biogas. How does this process happen? And here you can see the several steps you can have during the process. You start from biomass that in general consists of three main parts: proteins, carbohydrates, and lipids. Okay, you have these three big families. Then we have a first family of bacteria, hydrolytic bacteria, that cut these complex components into more simple components. For example, carbohydrates are transformed into simple sugars. Lipids are transformed into fat acids. Proteins are transformed into amino acids. Then another family of bacteria, fermentative bacteria, use these residues and transform it into volatile acids, into another simple components. Then another family of bacteria transform it into hydrogen or acetate. And finally, the final family of bacteria, methanogen, metagenic bacteria, use this substance, this residues from the previous process, and transform it, obtain energy, and transform it into methane and carbon dioxide, so into biogas. This is the process. So it's a very linear process, because it's linear in the way that every family of bacteria use a feedstock and have a residue used from another bacteria. So the bacteria families moves in a linear way. Okay, it's another way to see the process. So here you can have the description, probably more detailed description I give you, just to see the final reaction. So this is acetic acid, and the final family of bacteria use this acetic acid and produce methane and CO2. Okay, of course, it's not only this one the reaction we have a lot of reactions inside the process, but the main reaction and the most considered reaction is this one. Okay, of course we can have also other family of bacteria in competition that can produce other components. So it's more complicated than my description, but of course this is the considered pathway we have into the process. And this is the final composition of biogas. So you have a quantity of methane, which is the most considered component, that usually is between 15 and 80%, and the same in the composition of anaerobic, the composition of CO2, which is from 50 to 20, of course, depends on the quantity of methane. And then a lot of other components you have, but in very low percentage. The low heating value in biogas depends on the methane quantity, of course. If you have 50% of methane, you have 4,500 kilocalories per cubic meter. If you have a higher quantity of methane, you have a higher low heating value, because it's proportional to the methane content. Okay. Please look at this composition also in the new pathway, quite new pathway we can have. And so you can use biogas, of course, and we will see this now for the production, direct production of electricity and heat. But you can also think to separate methane from the carbon dioxide and the other components. So you can also obtain biomethane, 100% biomethane, and so using biomethane in every use of fossil fuel methane. So you can use biomethane and you can put into the national pipeline for methane, and so you can use into your house biomethane for your boiler or for your kitchen, or you can use biomethane into the car fed by methane. So this pathway can also goes to obtain 100% biomethane. Okay, yes, of course, when you have biomethane, you use it in a turbine or in a diesel system to produce energy. Okay, to produce energy. Sorry, there is a two missing here because you don't have to obtain CO, but in general you obtain carbon dioxide directly. Okay, so you should add here a two, so you produce of course CO2 and water. Okay. Just to to introduce other parameters for anaerobic digestion process. For example, you can consider the process temperature. You can work with temperature lower than 20 degrees. You can work with temperature between 20 and 40, or maybe more higher temperature. Of course, you have to change the bacteria family that works into your digester, because of course here in this kind of level you have certain kind of bacteria. If you work in higher temperatures, you need other families of bacteria, and in general we work quite heavy with this range, with mesophil bacteria. Of course, you can also decide what is the solid fraction in your biomass, and you can have dry digestion, wet digestion. It depends on your on your choice. You can have also only one reactor, digester, where every process occurs. So you have a unique digester where you have hydrolysis, fermentation, methanization in one step. Okay, so there are a lot of bacteria families that lives and use the residue of the previous family. Or you can have two, in general, two reactors. In a reactor, you have hydrolysis and fermentation, and in a second reactor, you have the final steps of the anaerobic digestion. You can also have a batch process. So batch process means that you put biomass inside the digester, you wait in general 20-30 days until the process is completed, and then you put away the residues and put new biomass. Or a continuous process where you put biomass into the process, and there is a sort of moving, a biomass moving. So you put okay, I will show you it's better in a few slides. So you can see the process. So you can see the time in days and the percentage of biomass used for biogas production. So you can see that in the first day there is a very, very rapid increase of biomass use. Then when the family of bacteria is very, very big, there is a decrease because the food start to decrease, and so the bacteria produce less biogas, biomethane, and so for example here you can stop because it's not economical interesting to continue here where the production is very, very, very low. So for example the typical time of of the process of the anaerobic digestion process is 28 days, 4 weeks. Okay, Okay, of course, the pH is important to control, to make the bacteria live and replicate. And this is the complete system. So you can see the biomass you can use, the digester where you produce biogas, then you can store biogas into a gasometer and use it, for example, into an engine to produce electricity and to produce hot water. A part, as just I said, a part of this heat is used for the digester. You have seen that typical temperature are between 30 and 35 degrees, and it means that for the large part of the year you must heat the digester. In winter, in autumn, also in spring, during the night, and so that there is a large quantity of heat you have to use for the digester, so for the process, and the other part you can use it for heating or other use. We can continue here. You have seen that there is a not degradable part for bacteria, for example, cellulose or other component, and so you can recover also this residue, and a part could follow aerobic digestion I mentioned before to produce a compost or fertilizer, and also the liquid part rich in nitrogen could be used for fertilizers, and so you can use all the residues to come back to the field, yes, you can, of course, you can reuse every final products. So biogas and of course also the residues digested. Okay, there are a normative law that give you information how you must work with this process and how much quantities you can use into fields, into lands. So you have to follow the local, regional or national law. So this is the batch systems, and which is the most common system you can see. I think you just have seen this kind of digester with this half sphere where you store biogas, and in the lower part there is biomass that is used from bacteria. You can also have a system for better distribute biomass along the digester, and this is the continuum system. Here you can see that it's a sort of cylinder where you put in continuous biomass from side. The biomass flows along the cylinder. So, for example, here you should have the hydrolytic bacteria, and then the other families until the methane bacteria. Okay, and so you have the final digestate at the end of the system, and of course biogas recovered from the upper part of the system. It's not so common, but interesting because it's slowest than the traditional biogas plants. So could be interesting because the impact is not so important like biogas plant that are 15 meters tall. This is 2 or 3 meters tall, so it's interesting from this point of view. Okay, I go very quickly because I just treated all the important things I would like to share with you. If you want, you can also find more detailed informations for example, for the cleaning, biogas cleaning, because if you use it into a turbine or into an engine, you must clean biogas, because some components could be dangerous for the turbine or the engine. So you should separate methane and also CO2, because it's not important for the reaction, from other pollutants that are dangerous for the energy system, like sulfur. Sulfur is very dangerous for the turbine, for example, because can break down the turbine. And these are some systems that separate the pollutants. And finally, the diesel or the turbine for the production of energy. So another way to use a gaseous biofuel. I would be happy if I also transfer to you this interesting information. In general, gaseous fuel or biofuels are better, liquid or gaseous biofuels are of course better than solid biofuels. And so gasification or anaerobic digestion are used for this goal, to transform a solid biofuel to a gaseous biofuels that can be used into engines and into turbines. And you can't use, of course, directly a solid biomass or a solid fuel into this kind of energy conversion system. So this is the reason of some of the processes, thermochemical, both and biological, you have seen into this presentation. Okay, I don't talk about mechanical processes, because there is not so many information to know. We just say that it's a physical process that allow to mill seeds and to extract oil. So I don't have so much information to give you for this process. So you can use, for example, sunflower, soybean, and so on to recover seeds, of course, and to a mill to produce oil. And you can use directly oil into an engine, a diesel engine, because you have a liquid biofuel to produce electricity and heat. Or, and this of course is a more interesting process that we will see next lesson with biofuels, you can use oil in a chemical reaction, transesterification, to produce biodiesel, which is very, very similar to diesel. And so you can use it, and we usually use it into our cars in a small fraction, but if you see B7 into the distributors, it means that there is up to 7% of biodiesel in diesel. But this will be the topic of the next lesson, where we speak about biofuels and bioproducts. Okay. Okay, I think we can also stop here, if you agree. Okay, so thank you. Have you any question?
Just one question. This is Simona speaking. Sorry about annoying you with all these questions.
No. You are welcome.
Okay, thank you. The question is regarding the anaerobic plants installed in Italy. Are they used to produce biomethane and then use biomethane as methane? Or are they used to use the methane with an engine to produce electricity and heat, usually?
Okay. The answer is very simple because, yes, anaerobic digestion plants are working since for 20-25 years, and all these plants were built for energy, directly energy production, electricity and heat. In the last years, but we are speaking about the last 2 or 3 years, maybe, it is possible, the law allows to produce biomethane and introduce biomethane into the national pipeline. And so this is the reason why some plants, also some existing plants, are moving towards biomethane production. So there are some existing and new plants that now are moving to biomethane production. Yes.
Also because for the accumulation, for the storage of the methane is much more easy.
Yes, but probably the best way is to introduce the best way, also economical, is to introduce biomethane into the national pipeline, or to store it, but store just to transport biomethane to distributors for cars feeding. Otherwise, if you are meaning that store biomethane and use biomethane for energy production, it's not convenient. So if you have to do another step that costs in terms of money and of energies to produce in the same place, in a turbine or into an engine, electricity and heat, it's not convenient, because you have another process, but you have the same quantity of methane, because you have only separated CO2. So it's not convenient in both for the energy and to the economic point of view. You have to introduce it into the pipeline or store it to transport to distribution for transport systems.
Maybe the best is to store it as a methane, I think.
Sorry?
Maybe it is more convenient to store and to use the methane rather than produce energy on the place, because
of course, absolutely,
okay.
Definitely, yes.
Mm-hmm.
Okay,
Thanks.
Other questions?
Thanks.
Welcome. Okay, so we can stop with the lesson, and we will start again next Wednesday at 9:30.